Hello, everyone. Today we'll talk about in further experimental evidences for SN1 and SN2 mechanism. In previous discussions, we have discussed about and we have seen what is the difference between the SN1 and SN2 mechanism. And of course, there is a question that how we can predict that certain nucleophilic substitution reaction is following the SN1 mechanism or SN2 mechanism. So for this, we have this very informative and detailed lecture. So I would emphasize that you should pay attention towards it because from this lecture you are able to get the full concept that how we can predict that either a reaction is choosing or preferring the SN1 pathway or SN2 pathway. So for the generally, whenever there is a hypothesis and the chemist has um, planned or envisioned that could be the possible opportunities or that could be the possible pathways for a certain reaction to proceed, so they do set up some of the experimental reactions, then they study, they examine, they analyze these one, and from these experimental evidences, they either prove that hypothesis or disapprove that one. So this is the general and the basic understanding that in any of the scientific project and in any of the scientific study, and particularly when we're talking about the chemistry. So when there's a nucleophilic substitution reaction, so chemist has work for the 6 and 7 conditions and the parameters. So they wanted to notice and observe because they have developed a hypothesis that these could be the factors which influence the SN1 pathway or SN2 pathway. But now there was a question that either some of really matters and some of the factors really matters, or some are basically not having any impact on these one. So that was conducted, that analysis has been conducted and studied through the experimentation, then using the different specialized instrumental techniques, and then statistics. So they were able to find out um, that there are certain factors which we are going to discuss in this lecture which influence SN1 mechanism and SN2 mechanism. So for proving and disapproving that hypothesis, so they basically have established a list of some of the questions. So the very first thing was that what are the kinetics and the stereochemistry of SN2 and SN1 mechanism. Now the second thing was that one, so is it does the structure of haloalkane have any impact or effect on the rate of reaction? What effect does the structure of the leaving group have on the rate of reaction? What is the role of the solvent? Is that solvent is also influenced that either a reaction is going to the SN1 or SN2? What effect does the structure of the nucleophile have on the rate of reaction? And lastly, under what conditions are skeletal rearrangement observed? As an organic chemist, as the students of the organic chemistry and the synthetic chemistry, we know that the molecules do undergo some of the skeletal rearrangement, which make them more stable for the stability reason, for the energy maintenance, and of course, generally it comes under the stability. So to have the best confirmation of them. So that we have to observe that under what conditions the molecule will go through the skeletal rearrangement, and that skeletal rearrangement is basically preferring this or giving the opportunity to that reaction either to go for opting the SN1 mechanism or SN2 mechanism. So another one, we can say that these are the established factors which have influence, which affect the substitution reaction. And then there is the prediction. We can make a guess and we can have make an educated prediction educated guess that is this reaction is happening to the SN1 or SN2 reaction. So our first discussion would be about the kinetics, and we will discuss the kinetics and gradually one by one structure of haloalkane, leaving group, solvents, nucleophiles, skeletal rearrangement, and stereochemistry. So now we are going to discuss about the kinetics of SN1 and SN2 mechanism. Very important to decide that the reaction is happening through what order of reaction, what are the kinetics involved in SN1 and SN2. So, by looking at the detail of the kinetics of these both mechanism, so we are able to see, and we can predict that that reaction is probably going through the kinetics SN1 or SN2. But of course, at this moment, kinetic is not only the factor. So whenever we are making a guess, we are making a prediction about a reaction that either that is SN1 and SN2. We have to see collectively all of the factors, that what is a haloalkane, what is a solvent, what is a nucleophile, what are the kinetics, what is a stereochemistry. So then on analyzing all of these factors, then we can have the right prediction that either that reaction is a SN1 and SN2, without going into the mechanistic experimentation, because that already scientists have established. They have done that with the non substitution reaction types, that what are the strategies, what are the pathways, what are the intermediates, possible intermediates, what are the possible transition states they are going through. So then now studying these factors and their experimental evidences, we are able to predict that this reaction is happening to the SN1 or SN2. Now, coming to the point, the kinetic order of nucleophilic substitution can be studied by measuring the effect on rate of varying the concentration of haloalkane and nucleophile. As we know, these are the key reagents in any of the nucleophilic substitution reactions. So, by looking at the order, means that at certain time, what is the rate of um, disappearance or appearance of any of these reagents. So, those reactions whose rate is dependent only on the concentration of haloalkane are classified as SN1, because there is only the haloalkane which is involved in a rate determining step. Those reactions whose rate is dependent on the concentration of both haloalkane and nucleophile are classified as SN2. That are the two things which we already have built from our previous discussions. That, of course, in SN2, which is a single step reaction, there is the bond breaking of the carbon and the leaving group and the attack of a nucleophile. So the both things are happening at the same time. While in SN1, which is a two-step reaction, so the very first step, which is a rate determining step, is the formation of a carbocation. Now, we will talk individually in more detail. Firstly, the SN1 kinetics. Because the transition state for formation of carbocation intermediate in an SN1 mechanism involves only the haloalkane, which is R leaving group, and not the nucleophile. And this step is the rate determining step. So this is a unimolecular process, because only the one molecule is involved, whose concentration is basically for the rate determining step. So the result is the first order reaction. So SN1 reactions are the first order reactions. So here we can see from the example. So for SN1, we have picked one of the tertiary haloalkane, that is the tertiary butyl bromide, its common name, and its IUPAC name is 2-bromo-2-methyl propane. So the rate determining step is the formation of carbocation. Then there is a Br negative, and then there is an entry of a nucleophile. So here the methanol we are using as a nucleophile and as a solvent. So what would be the next step? is, of course, the attack of that nucleophile from this oxygen, which is rich in electron. So this is basically the pointing site, which is making a bond and giving that electron, non-bonded or lone pair of electrons to the carbon. So here, this is the oxonium intermediate which has formed. So there, that extra hydrogen has to remove, and that will be picked by the methanol which is already in the system. So the thing is this one, that there is the 2-methoxy 2-methyl propane, that is our product, right? And from this we can find out the rate of this reaction. So the rate of this reaction is basically determined by the differential rate law equation. So here you can see this differential um, fraction of the concentration of the reactants and with the dt of over the time, which is giving you the idea that this is the function of a time. The k is the rate constant, and here this is only dependent on the concentration of the haloalkane. So in this instance, the rate of reaction is expressed as the rate of disappearance of the starting material, which is a 2-bromo 2-methyl propane. The rate has no dependence on the concentration of the nucleophile. So we can conclude that any substitution reactions whose rate depends only upon RLV proceed via an SN1 mechanism. So what does it mean is, because here the carbocation, if that will be formed, so that is a rate determining step. So then whatever the nucleophile, either that is stronger, either that is a weaker one, so that will attack on that carbocation. So what we are examining, what we the scientists have experienced during the experimental studies of these kinetics, that there is the rate of reaction is basically determining or depending on the disappearance of this haloalkane into an intermediate, the carbocation. So this molecule is disappearing because now this is fragmented into the carbocation and a Br negative. So that is basically deciding, and then eventually it is going through this nucleophile attack and finally in a product. Now you can see that here what we have formed as a product, if we wanted to mention the class of the compound, so this is the ether, right? So the nucleophile is very important to decide that what our target product is. Either we wanted to go any of the alcohol from the haloalkane, or we wanted to go for any of the ether. So we will pick some of the nucleophile which has an R group to give ROR functionality to that compound. So then that will be the ether formation. Now the differential rate law for a first order reaction is basically, so here you can get that what these values are mentioning. So either that is a first order or second order reaction, but I am explaining these with this first order reaction, that what each symbol is mentioning. So K is the rate constant of the first order reaction whose units are per second, because this is relative to the time, the concentration of the reactants with the time. So brackets with A is the journal notation for any of the you say the reactant, and here this is the haloalkane. So denotes the concentration of the first order reactant A. Now the dA divided by dt denotes the change in the concentration of the first order reactant A in the time interval dt, and the negative sign is basically to give you the idea that this concentration is decreasing with the passage of time. So that is basically the mathematical information about how that equation has derived. So we are not going into the whole derivation and differential detail of these one. So I wanted to emphasize that how this comes to and what this equation states to you. So now we are going to the Sn2 kinetics. By contrast, there is only one step in Sn2 mechanism. If we compare with the Sn1, where this is a the unimolecular, and now this is a biomolecular reaction. Here, the bond breaking and bond nucleophilic attack is happening at the same time. So there is no stable carbocation formation is happening because these both events are happening at the same time. Uh, why? The reason is this one, because these primary haloalkanes or the methyl haloalkanes are not such stable that they could afford the stable carbocation formation. So here you will see whenever there is an example and we're generally discussing the kinetics, so we pick that particular haloalkane which is favoring the SN1 or SN2 kinetics, right? In later discussions, we'll talk about that what would be um, the cases in case of the secondary haloalkanes, which can go on the both sides. So what are the deciding factors, right? So here, this is a bromomethane, which is a primary haloalkane, and this is reacting with the sodium hydroxide. So this will be ionized into the Na positive, OH negative, and then this hydroxyl is attacking on this one. And now you will see here we get alcohol, methanol, because this was not attached with any of the R group. So this was not ROR, this is basically ROH. So that's why this is the alcohol functionality, which we have created from the haloalkane as a starting material. Now, if we talk about their rate of reaction, so the rate of reaction is determined by and dependent on the nucleophile and the haloalkane. So here, this is the minus D concentration of haloalkane divided by dt, and same for the hydroxyl ions, right? So overall, this rate of reaction is dependent on the concentration of methyl bromide and hydroxyl one. So it means if we double the rate of these both reactants, then the rate of reaction will be 4 times, right? Or if we double any of these ones, so that will be double. But in case of the SN1, which we have studied, if we increase double the concentration of a nucleophile, so that has no impact on that reaction. Now, at the end, there's a task. The reaction of bromomethane with azide ion in methanol is a typical SN2 reaction. So what happens to the rate of reaction if N3 concentration is double? So you have to answer this task, that either you get that one, that what is the rate of reaction of SN2 and how that nucleophile impact SN2. So that's for today. Have a good day. Thank you.